And the earlier the better, because it sucks to have to go through a textbook with you that I haven't been able to all the way go through myself. Anyways, today, metric spaces. So last week we finished with homeomorphisms. Today we're jumping kind of like a massive shifting gears. Today is almost something that you could just jump in if you hadn't been here for the entire class type stuff. So kind of a standalone little section. And you'll notice that we reproved some stuff that we already did, but now we just do it in a slightly more general way, and it doesn't even change the proof. So I think this will be really quick. Metric spaces are already pretty intuitive, so we'll just jump right into it. So talking about metrics and metric spaces, definition, what is a metric? Intuitively, you know what a metric is. It's a way of measuring distances. And so you've used metrics tons of times before in measuring distances. And you notice that sometimes you need to be a little bit careful about how you measure distances. For example, when you talk about how far is it from here to wherever your house is, you wouldn't just measure, drop a pin here, drop a pin at your house, pull a string between them and measure the string, because you have to follow roads and stuff like that. So there's a little bit of subtlety there on what exact metric you were using to measure that distance, and we'll get an example, something like that. But ultimately, metrics, you can pretty much think about them as a way of measuring distance between points, and your intuition will be spot on. So let's define it exactly. A metric on a set X is a function, d, from x cross x to r. So it's going to take two members of x and spit out a real number, a distance. That's what it's going to do. So d is a function, consumes two members of x, and spits out a real number, where x is what you're defining the metric on. So d is a metric if it's a function like this, and it satisfies these three properties. Property 1, d from x to y is always greater than or equal to 0. The distance between 2 points is always greater than or equal to 0. Furthermore, it's equal to 0 if and only if x and y are the same point. So I can't have two separate points and have the distance between them be 0. If the distance between them is 0, they are the same point in order for it to be a metric. Property 1 makes sense? Mm-hmm. Property 2, the distance from x to y has to equal the distance from y to x. Pretty intuitive. Doesn't matter which way you measure the distance, get the same thing. And then finally, the triangle inequality. The distance from x to y plus the distance from y to z has to be greater than or equal to the distance from x to z. You can't have, so here's x, here's z. If the distance from here to here is 16 miles or whatever, there can't be some shortcut I can do like that, where I stop at some other point here that made the path shorter. I can't go like this and have my total path here less than 16 in order for it to be a metric. Okay. So the distance from x to z has to also be the shortest distance that you can get from the metric in order for it to be a metric. Does that make intuitive sense? Yeah. And we already talked about why it's called the triangle inequality. First time it comes up is in geometry with triangles. And what it says is that if you have a triangle, the length of one side is always greater than or equal to the length of the sum of the other two sides. Less than or equal to, sorry. So if this is distance A, this is distance B, this is distance C. C is less than or equal to A plus B, where you allow the weird case where we have a straight line triangle. If you don't allow the triangle to basically just be a line segment like that, then we'll get rid of equals. Make sense? Mm-hmm. So that's what this is saying. The distance from x to y plus the distance from y to z has to always be greater than or equal to the distance from x to z. And now we call x with d, x with some metric, a metric space. So a metric is a type of function. X with a metric is a metric space. And we're used to talking about word pairs like that as spaces, right? Yeah. Just like we had a topological space that was x with a topology t. Now this is x with a metric d. Metric space. That's all it is. Pretty straightforward idea. So let's play around with one. Let's look at a metric that we know and love. Let's look at the metric d from r cross r to r. so it takes two members of R and assigns them a real number, by the distance from x to y is equal to the absolute value of their difference. This is the exact notion of distance that we use just on the real number line. Got the real number line, you want the distance from this point to this point. This is exactly how you do it. If I said, what's the distance from 5 to 8, what's the distance? 3. How do you calculate that? You can either take the absolute value of 8 minus 5. Well, it's 8 minus 5, 3. Take its absolute value, still 3. Or you could take the absolute value of 5 minus 8. What's 5 minus 8? Negative 3. Take its absolute value, 3. The absolute value of the difference between 2 points gives you its distance. So that's what we're saying here. So let's go over just this one in full details. We won't bother doing any other metrics that you're used to, but we'll do this one in full detail just to make sure that we aren't accidentally covering up any subtle detail. So first off, let's check, is this thing actually a metric? So first off, is the absolute value of x and y always greater than or equal to 0?
Yeah.
Yeah, by definition, the absolute value function, right? And when is the absolute value function equal to 0? Only when the absolute value of the thing you're taking is 0. Right? So, observe that absolute value of x minus y is greater than or equal to 0 by definition of absolute value. And that the absolute value of x minus y is 0 if and only if x is equal to y. The only time the absolute value function is 0 is when what's inside is 0. So that means x minus y equals 0. When does x minus y equal 0? When x is equal to y. Just transpose y to the other side. Make sense? Alright, let's look at the next property. This one's pretty obvious. Observe that the distance from x to y is equal to the absolute value of x minus y is equal to the absolute value of y minus x is equal to the distance from y to x. Good?
Yeah.
Mm-hmm.
And then triangle inequality. We're going to do an ugly way of showing that this holds. There's a more elegant way. We probably had time today that I should have just done it that way. In analysis, we proved the triangle inequality in a much nicer way. This one, we're doing a way where we handle all 6 cases. So let me tell you what I mean by all 6 cases and then show you what we're doing. So let x, y, and z in R. And there's 6 possible cases for how we can plug in x, y, and z here. Right? We have 3 options for what goes here, and then 2 options for what goes here with the remaining one going here. 3 times 2 times 1. We could have x is less than or equal to y is less than or equal to z. We could have had y is less than or equal to x is less than or equal to z. We could have had z is less than or equal to x is less than or equal to y, etc. There's 6 possible ways we can fill this out. So we're just going to show for one of the cases, here's one of the cases, here's how the triangle inequality comes out. In fact, it doesn't, let's let you guys pick one because maybe that will help it appeal to your intuition. So we'll erase that, and we'll erase that, and we'll get that. Okay, so distance, what order do you want them in? What one should come first?
Y.
You want y here, then what?
Z.
Then x. Alright. So, let's fill this out. So assume that y is less than or equal to z is less than or equal to x. The bit of analysis that we're using behind the scenes here is that x greater than or equal to z means x minus z is a positive number. Those are the same thing. 3 is greater than 2 means 3 minus 2 is a positive number. That's how we define greater than in analysis. So then let's go through this. So the distance from x to y plus the distance from y to z. So first off, the distance from x to y, what is that going to be? That's going to be x minus y.
Yeah.
Good?
Mm-hmm.
The distance from y to z, that's going to be z minus y.
Shouldn't those be absolute numbers? Or are they supposed to be parentheses?
Notice that I put it bigger minus the smaller, so it's always positive.
Okay.
It doesn't matter what order I do it in, that or the same thing. So I can subtract it in any order I want. If I always do the biggest minus the smaller, then it's already positive. And so we can ignore the absolute values.
Okay.
That's why these 6 cases, this is a hideous way to do it, but it's an easy way to do it. If you get one of the cases, you can list them all out. It's just boring. Anyways, so then the distance from x to y plus the distance from y to z. is equal to x minus y plus z minus y. Did we do that right? Distance from x to y is going to be x minus y, and distance from z to y is going to be we did a weird one. I didn't think this through ahead of time. Let's see. Because when we write this out, this is going to be equal to, nothing cancels this time. So we picked a case where these terms don't cancel, so let's see. We're going to get x minus 2y plus z.
Is it always going to be the distance between x and y and the distance between y and z, even when you move them around?
If we have it in this order, this is their distances, right? X minus y is this distance, and y minus z is this distance.
I think if we choose different distances, then the terms will cancel out, but
Yeah, that's what I was wondering. Is it because we changed the order of x, y, and z, won't matter?
Let's
What
see
distance
where
is
we're
it?
trying to go here. So let's just erase this so that we're not trying to plug into my stuff. Maybe that's just a bad idea to do. Let's just think about it this way. So let's see. We're trying to show that this is ultimately greater than or equal to x, y, y, z is xz. What's xz? That's x minus z, right? So x minus z, and let's see what this is equal to. Let's write that out. We're going to have x plus z, x plus z,
Oh wait, aren't we trying to show that those are less than, not
Greater
greater
than.
than?
greater than or equal to. The distance, if you go from x to y, then y to z, better always be greater than or equal to your distance if you just go straight from x to z.
Okay.
Did I write it wrong up here?
we're on a number line, right? I don't even think that's possible. For you to go to x, do the distance from x to y.
You can, and it's something like this. Here's x, here's z, here's y is one of your weird cases. So your
No.
distance from x to y is all that, and then your distance from y to z is that.
I know, but we don't have negative distance, so you're just adding two positive numbers.
Yeah, you're adding, so it's positive,
And you want it
but
to
it's
be
much greater than.
Oh, okay.
So it's not necessarily equal, I thought is what you're saying.
Yeah, that's what I was trying to say.
Yeah, okay, so x minus z, let's see. X minus z, since z is greater than or equal to y, we know is definitely less than x minus y. This is x minus 2y though. Keep that here. Is x minus y. Okay, there we go. Which is going to be less than or equal to x minus y plus z minus y, which is equal to that. Okay, there we go. Did it. So let's go over it real quick in case that made 0 sense, because it probably didn't. Making sense? Let's rewrite this out. So this is equal to x minus y. Is that the distance we're ultimately getting?
I think
No, we
it's
want x minus.
So x minus.
Shouldn't erase that. X minus z is where we're ultimately going. X minus z. Now, but I knew that this was less than or equal to x minus y. I knew that was less than or equal to x minus y plus z minus y.
So
Because
now
that
we
was
just
adding
need
something.
a
Okay, so
less
maybe
than or
we can
equal
just
to
use it
sign
there.
instead of equal sign.
Yeah, so this is equal to this, right?
Yeah.
And then z minus y is a positive number, so if we get rid of that, we could have only made it smaller. And then z is bigger than y, so if we subtract z instead of y, we could have only made it smaller.
That makes sense.
And that's proving it in that case. And then you can prove for all 6 cases, which is a terrible way to do it. There's a way nice way to do it. With absolute values, that we do an analysis. So if you go look at my calc series, it's going to be probably the first lecture, right?
Yeah.
Maybe the second lecture, where we actually prove out all the properties that the absolute value function has much more nicely than that. But triangle inequality is one of the things we prove out. Okay, so that was that one. Now let's look at 3 more and get some intuition for what these are saying and get some intuition for the fact that they're true. So another metric, we're looking from a point in R2, a point in the real number plane. Notice how this is R2 crossed with R2, so we're going to talk about the distance between 2 points. Oh, I forgot to say to R. Oops. I forgot to say to R on all these. This is arrow to R. This is arrow to R. This is arrow
So
to
you're
R.
going to be dealing with 2 sets of coordinates, basically.
You pick 2 points in R2 is your input.
Yeah.
Yeah. So instead, because you could also write this as R cross R cross R cross R, but then that's a terrible way to write it for what we're doing because you might get confused. So I wrote it this way to try and make it very clear. X is a point in R2 and Y is another point in R2.
Yeah.
You plug in 2 points in R2 and it's going to spit out their distance. And the distance function that we're going to use is the Euclidean distance function. I think we show in this class how this comes from just Pythagorean Theorem.
Yeah.
So same thing as a Pythagorean Theorem, just gives you the distance between 2 points on a plane. So first off, notice the distance between 2 points on a plane is always greater than or equal to 0. We're taking the square root, so can't take square roots of a negative, otherwise we get something imaginary. And our function is just the real numbers. So this can't ever spit out negative value. Notice that the only way that this thing can spit out 0 is if this piece is 0 and this piece is 0. The only way this piece is 0 is if x1 is equal to y1, and the only way that this is 0 is if x2 is equal to y2. And so the only way the whole thing's 0 is if they're the exact same point. So that's the first property. Second property, since I'm squaring a difference, it doesn't matter if I flip the order of those, I'm still going to get the same value out.
Right.
So it's symmetric. Triangle inequality, we prove that in geometry for this one. Because that is the distance of the sides of the triangle, and so the triangle inequality that you prove in geometry is literally for the Euclidean metric. No surprise there, right?
Okay.
So that one's the one that we know and love, the one we're used to. That's one that we typically work with. But let's do another one real quick. Now let d sub t. This is called the Taxicab Metric, and it's going to be the one that drives city blocks, driving on squares. Its distance is going to be given by the absolute value of x1 minus y1 and the absolute value of x2 minus y2. So if I want the distance from here to here, and we're on some xy coordinate plane, so xy system, the distance from here to here now is this distance plus this distance. So it's like we're driving on roads, and we can't just drive straight from here to here. x1 minus y1, that's the distance we went here. x2 minus y2, that's the distance we went here. If this is the point x1, x2, and y1, y2, right?
That makes sense.
Oh,
But what if there's like more than
I did it kind of weird. It's because I have my xy here, and so I kept the x's associated with the x point and the y's associated with the y point. Yeah, this is not x1, y1, and x2, y2.
Oh, that's how you usually
Oh,
do it.
what the?
Yeah, that is the way you usually do it, but since I called my points x and y, I'm saying this is the first coordinate of x, and this is the second coordinate of x. Because x is a point. So this is a point x, this is a point y. Y's coordinates are y1, y2, x's coordinates are x1, x2. Okay, so that probably clears up some confusion, right?
Yeah.
Okay. Yeah, probably should have done p and q and just expressed them in terms of x1, x2. or x1, y1, and
What
x2,
if there's
y2.
like more roads than just two?
Huh?
You're saying this for like roads and stuff, but like what if there's more roads than just two that you go on? So instead of
Well,
just doing the distance. you're-
notice that we could have also done this and we'll get the exact same thing. Add up all those distances, that's this. Add up all those distances, that's this. And remember, it's in some sense meant to give you the shortest. Same way that the Euclidean metric gives you the shortest distance between 2 points. This is the shortest your distance could possibly be if you're in this grid layout. Because maybe this is a valid street and for some reason you have to go like that. Right? But the minimum distance. Okay, so that's the taxicab one. And then this next one is called the max metric. This one's kind of a weird one. We just take whatever is bigger out of these two things and call that the distance.
Why?
Why do you do that? Yeah.
I have never come up with a use case where this was a useful thing to do. The fact that it exists as a common one means that there's probably some set of problems where it's a useful thing to do. But nonetheless, it is one.
So you like
Oh, let's continue talking about this one first to make sure we see how it satisfies the three properties. We went off on a tangent with the coordinates. So first off, the distance is always greater than or equal to 0, right?
Yeah.
And it's equal to 0 if and only if those are the same points. If they differ in any x or in any y, then you're going to add that component. Maybe looking at this makes it more obvious that they're only equal when this is 0 and this is 0. Okay. Triangle inequality holding for this one. You know triangle inequality holds for absolute values. So, yeah, holding for sums of absolute values. Nothing surprising there. Symmetric. We skipped symmetric. We already know that absolute values are symmetric, and so nothing surprising there. Okay. Now, the third one is basically the exact same as the second one, except for we only take the max of those two numbers.
Okay.
So the distance between this point and this point, and this point and this point, and this point and this point are all the same.
Nice.
Because the distance from here to here is this distance, the distance from here to here is this distance, and the distance from here to here is this distance. It takes the max of what's bigger between the displacement in the x and the displacement in the y.
So
Here's the displacement in the x, here's the displacement in the y. Which one's bigger? The displacement in the y. That's the number we assign. Let me draw one more point to help hammer the point home. What's the distance from this point to this point? It's whatever this distance is. Because in that case, our displacement in the x is bigger than our displacement in the y. Takes the max of whatever's bigger, our displacement in the x or our displacement in the y, and calls that the distance.
Okay.
Make sense? Okay. So we'll come back to these three themes and try to help give you more intuition, especially for this one. I think when we talk about topologies these things generate, I think that this one will make a lot more sense. But let's continue. Definition. Okay, so let XD be some metric space. For each little x and big X, and for any positive number epsilon, we define the open ball with that metric, centered at x with epsilon, to be the set of all points y within distance within epsilon of x. This is exactly how we defined open balls before. It's just when we were talking about open balls before, our distance function was always the Euclidean metric. Now we're defining open balls again, where our distance function is any metric, and whatever metric you're talking about, you put it right under the open ball. Does that make sense? So this open ball is still the set of all points within epsilon of x. Make sense?
I think so.
Okay. And the closed open ball, and the closed ball, is defined the exact same way. We just replace the less than with the less than or equal to. So, in regular old Euclidean notions of these things, an open ball still looks like this. the ones we were already talking about, x, epsilon, and the closed ball is that exact same thing except for we include the boundary points.
Yeah.
But now we just have it for any metric. So, more general notion of something we've already been talking about. And that's what I meant by our proofs. We're going to be proving things we've already proved, just now referencing this as a general metric instead of the Euclidean metric. And it doesn't change our proof at all. Anyways, so feel like you understand what the open balls are and the closed balls are?
Yeah.
Alright, so quick lemma before we prove this thing, lemma that we've already done. Let xt be some metric space. If y is in the open ball centered at x with radius epsilon, then there exists some delta in R such that the open ball centered at y with radius delta is a subset of the open ball centered at x with radius epsilon. And I forgot to call my little d's in here. I'll probably do that over and over again. But those should all have little d's under them. So let's draw a picture of what we're seeing here. So here's some open ball. Oops, we need an open ball. Here's some open ball centered at x with radius epsilon. We're saying for any open ball like this, and for any point in it you pick this point y, I can find some open ball around y with radius, so pick delta to be this distance. Now this open ball centered at y with radius delta is going to be a subset of this open ball centered at x with radius epsilon. So for any open ball centered at x with radius epsilon you pick, and for any point y in there you pick, I can always find a delta such that the ball centered at y with radius delta is a subset of the ball centered at x with radius epsilon. Does that make sense?
Mm-hmm.
Something we already proved. Let's do it again. So, if y is in there, blah, blah, blah. Okay, so let y be some point in an open ball centered at x with radius epsilon. And let delta equal epsilon minus the distance from x to y.
Yeah.
That's exactly how I drew it in my picture. Delta is equal to epsilon minus the distance from x to y. Good?
Mm-hmm.
Alright. Okay, so now I'm going to say that the ball centered at y with radius delta, I'm going to say that this ball is a subset of this ball, basically. That's what I'm going to argue from here. How am I going to do that? I'm going to pick a point z that's in this ball and show that that point is also in this ball. And therefore, the smaller ball is a subset of the bigger ball. Okay, so let y be in the open ball, let delta equal epsilon minus the distance from x to y, period. Okay, so here's where I pick my point z. Let z be any point in the open ball centered at y with radius delta. What does it mean for z to be in the open ball centered at y with radius delta? That means that the distance from y to z is less than delta.
Yes.
Right? So now I'm trying to argue that z is also in this ball. So I need to show that the distance from x to z is less than epsilon. If I can show that the distance from x to z is less than epsilon, we're done.
Okay.
Okay, so that's what we're going to be doing here. So let z be some point in the open ball. Then the distance from x to z, I'm trying to show that this is less than epsilon and we're done. So the distance from x to z, I know by the triangle inequality, is less than the distance from x to y plus the distance from y to z, right?
Mm-hmm.
That's just triangle inequality. We haven't used this fact yet. But now the distance from y to z has to be less than delta. Because z is in this open ball. What is this open ball? It's all the points whose distance is less than delta away from y. So the distance z is from y has to be less than delta. So when I take this and I replace this number with delta, I could have only made it bigger. So this right here is for sure less than this. With me?
Yeah.
Okay, what's our definition of delta? Epsilon minus the distance from x to y. So make that substitution. And then simplify. You see it?
Yeah.
Alright. That's it. So we just going to show that the distance from x to z is less than epsilon. Therefore, z is in the ball centered at x with radius epsilon. Therefore, this open ball is a subset of this open ball.
That's very similar to how we proved it before, isn't it?
It is identical. Well, I might have changed it because I just wrote it, but it's the exact same thinking. And then the second one is also something that we proved before, but we'll do it again. So next, let xd be a metric space. Then beta equal to the set of all open balls you can possibly create is a basis for x. Oh, this is the one that we did before.
Sometimes
We
you
should this one.
just listen to what you say instead of actually look at the board. Because what you don't all the time follow what you exactly wrote on the board, but it's better to just listen because then you understand it better when you say it.
I say it shorter because I don't want to say that whole thing. But I want you to understand what this is saying, right? For any x, you pick a big X, and for any epsilon greater than 0, create the open ball. Beta is a set of all those things.
Right.
And you're saying we haven't heard this already?
We have not proven that beta is a basis for any topology. We proved it when we were talking about the Euclidean metric, that the set of open balls was a topology for R. So we proved something very, very similar. This is slightly more, well, not slightly more, this is more generic now. And notice that this is now going to give us a way of generating a topology for any metric space. Because now for any metric space you have, I can create basis elements this way, and then I can use those basis elements to create a topology.
Yeah.
So just because you have a topological space doesn't mean you have a metric space. But if you have a metric space, you for sure have a topological space, which should make intuitive sense for how we think about topologies and metrics. What does a topology give me? All a topology tells me is proximity. It tells me if one thing is close to another thing. How close? Don't have a clue. All I know is either two things are close or they're not. Proximity is preserved in topologies. Topologies give me a proximity. Not proximities are preserved, sorry, that's homeomorphisms between them. But topology gives me proximity between points. That's all it gives me. What does a metric give me? A metric tells me how close points are together. That's what a metric gives me. It doesn't just tell me whether or not they are close, it tells me exactly how close they are. And so it makes perfect sense that if you have a metric space, there should be some way of getting a topology from it. Right?
Mm-hmm.
So we're showing that that's the case. If you have a metric space, you already have a topology you can get from it. You can induce a topology on that.
Why isn't it the other way around?
So in a topology, think about it this way. If we just have a topology and I give you 2 points, let's say I'm a topology, you feed me 2 points. You give me 2 points, and all I can do is answer the question. You ask me all I can tell you is, yes, those are close, or no, they're not close. You give me 2 points, I can tell you, yes, they're close, or no, they're not close. That's all I can answer if I'm a topology. If I'm a metric space, you give me 2 points, I can tell you exactly how close they are. Which means I should also be able to tell you whether or not they are close, right?
Okay.
So if I can tell you exactly how close any 2 points are, that's a lot more information than just knowing whether or not they're close.
Mm-hmm.
I can tell you exactly how close they are. And so if I can tell you exactly how close they are, I better also somehow have encoded in me a metric for telling if they are close, whatever close means. And we know what close means, right? We have intuition for what close is?
No.
What do you mean?
Yeah. You mean like close in the topology?
Yeah, close in topology.
Isn't it like something with open balls being and like what is it, the neighborhood?
Well, we usually think about it in terms of sequences. You remember how we define a sequence? A converging sequence is usually how we get our notion of proximity. It gets arbitrarily close to. means it approaches. And so with topologies, we're able to start talking about whether a sequence converges to a point or not. That's what we really mean by getting arbitrarily close. And so once we have a notion of convergence, we have a notion of closeness, of proximity.
Okay.
And we define in this class a sequence, and we define what it means for a sequence to converge to a point, or to get arbitrarily close to a point is one way that that's often said.
Yeah.
Okay. Anyways, but intuitively speaking, we know, okay, topologies give me proximity between points. Metric space gives me exactly how close two points are. There better be some way that I can get proximity from it. And there is a way. And we're going to prove that there is a way. That's what we're doing here. We're saying, look, if you have a metric space, here's a collection of sets that you can get from that metric space that are a basis for a topology. And you remember what a basis for a topology is?
Yep.
Right? Hopefully.
Yeah.
What's a basis for a topology?
It's like the basic elements that can build your topology.
Oh, yeah, and then you had the Lego.
Yeah, back to the
Yeah.
Lego analogy. If you think about every possible type of Lego piece as a basis element, and the topology is all possible Lego structures, then that would be a basis. Because any union of Lego pieces will give you any Lego structure you can think of.
Yeah.
Right. Okay, so let's actually do the proof now. So let's go over the proof one more time, make sure it makes sense exactly what we're saying. Let XD be a metric space, then the collection of all possible open balls you can create with that metric space is a basis for X, the set we defined our metric on. X is a set, D is a function, that gives us distances on that set, distance between 2 points in that set. Good? So, let's prove that the set of all possible open balls is a basis for a topology, and since it's a basis for a topology, it generates a topology. Do you remember what we had to show that something is a basis?
Yeah, it was like the union of open balls, the intersection of
I'm pretty sure that's just a topology.
Yeah, I think you're thinking of a topology. What's a topology? Topology is a collection of subsets such that the set and the empty set are in there. Any union of open sets is also in there, and any union and any finite intersection is also in there. But no, for a basis, to show that something is a basis, we need to show two things. One, we need to show that beta is a basis on X, we need to show two things. We need to show that for any point in X, there's a basis element containing it. That one's a pretty obvious property. The property that isn't quite so obvious is we need to show that anytime you have two basis elements intersecting,
There's a third basis.
then there has to be intersecting at some point, pick a point, there has to be a third basis element containing that point, such that it's a subset of the intersection of the two basis elements.
Yeah.
okay.
Remember that picture? We've done that a few times now?
Mm-hmm.
Alright, so that's what we're proving. We're proving that this set of open balls is a basis on big X. So we're going to prove those two properties. So I'll let little x and big X and observe that little x is in the open ball centered at X with radius 1. Right?
Mm-hmm.
Yeah.
Okay. So I just found for any little x you pick, I found an open ball containing it. And it doesn't matter what number I put there, right? Could have just as easily put 1/2.
Mm-hmm.
Doesn't matter.
Yeah.
Some number. That's still just an open ball, and it for sure contains that point. Good? Okay, so we showed that every point in the set is in an open ball. Okay, next is the one that's not as trivial. So let y be some point in the intersection of two open balls. So maybe draw a picture over here to keep our letters in mind. Which piece I do think? It's a little longer, it's a better one. So this point over here is going to be the point x1. This point over here is going to be the point x2. This has a radius of epsilon1, and this one has a radius of epsilon2. And y is somewhere over here. Good?
Mm-hmm.
So that's our picture so far. So let y be some point in the intersection of two open balls. Then, by this lemma, there exists delta 1. So first off, since y is in this open ball, there exists some delta 1 I can create. Delta delta 1 such that the open ball with delta 1 is a subset of this ball, and there exists some delta 2 I can create such that the open ball around this with delta 2 is a subset of this ball. That's what I'm saying here. So where's my other exists? Right here. So then there exists delta 1 and delta 2 such that the open ball centered at y with radius delta 1 is a subset of the open ball centered at x1 with radius epsilon 1. And the open ball centered at y with delta 2 is a subset of the open ball centered at x2 with radius epsilon 2. Good?
Now what do? Do you just intersect the two?
No, because the intersection of two balls isn't necessarily an open ball. So
Okay.
now I'm going to let delta equal the minimum of delta 1 and delta 2.
Okay.
So delta is for sure less than or equal to delta 1, and delta is for sure less than or equal to delta 2. Right?
Yeah.
So whatever my delta is, it has to be completely contained within this ball, and it has to be completely contained within this ball. Both these little balls here. Right? So it's a subset of both those. And since it's a subset of both those, it's a subset of both these, and
Okay.
therefore it's an intersection. That's where we're going with this. So let delta equal the min of those, and observe that y with delta is a subset of y with delta 1, and we already know that we knew that that was a subset of x1 with epsilon 1. Similarly, y with delta is a subset of y with delta 2, which we know is a subset of x2 with epsilon 2. So it's a subset of both of them. So then y is in the open ball centered at y with radius delta, which we know is a subset of the intersection. So it's in both, it's in their intersection. And therefore beta is a basis on x. Good?
Yeah.
Cool. Just a definition now. Let x d be a metric space. The topology generated by beta, the beta that we talked about up there, is called the topology induced by d. So once you pick a metric on a set, then there's a topology it induces. What's the topology it induces? It's the topology whose basis elements are the set of open balls, using that metric. So that's what we're saying here, is a topology induced by D, and is referred to as a metric topology, because it's a topology induced by metric, so we call it a metric topology.
Doesn't the topology have to not just have a metric space, but also an epsilon? Since that's what it requires to make the basis elements. Well, you said that let that be a metric space, and then let the basis elements be such that, and you required an epsilon to make those basis elements.
Oh, so remember what your distance function d is.
Yeah.
It is 2r. So it takes all the way back over here. Takes two things out of x, but it always maps to r. So my epsilon is always just something out of r. I know that my d function, my metric function, always spits out real numbers.
I'm saying, don't you need a metric space and that epsilon?
Wow. This is any epsilon you choose.
I know,
We're saying for any positive number.
but you still need one to make your basis elements, don't you?
In r plus. We need one to make,
Okay.
for a particular basis element, we have a particular epsilon.
Oh, is that saying for all epsilon in
Yep.
there? Oh, I thought that was just one epsilon. Okay.
Nope, for any. For anything out of there and for anything out of there. Pick any two of those, that gives us one.
Okay, then I see why you don't need a metric space.
Okay. I just realized I was drawing pictures over here when that's off my camera. Shame on you guys. Let me draw past my squiggly.
I actually did recognize it. That
And you didn't say anything?
was important.
It's always important. Okay. Why would it be important for you and not for those poor suckers watching the lecture? Which is back to just you.
So I'm a poor sucker watching.
And you're the poor sucker watching the lecture. I swear I had a bigger one. Maybe this is it.
Do you
Okay.
not have more chalk than what's there?
big pieces, which are garbage chalk. Maybe you could already hear that squeak, and then it doesn't erase near as good. No.
Oh,
I see what you're saying.
right.
Which
Yeah,
is
but
why
you have, like, more
you can see
chalk.
that someone was using it right here on the whiteboard. That was someone using the bad chalk. Can you see on the whiteboard where there's all those terrible marks?
Mm-hmm.
Yeah.
Yeah, that's this chalk, and you can feel the difference.
Okay, but
And it writes
do they
terrible.
not have more chalk somewhere?
Oh, you're saying over here?
Yeah.
There was one good piece that I found, and then after that I was picking out the rest are bad pieces. Maybe under here, I didn't check that. Ooh, there we go, that's a good one. You can tell by the feel. Just feels right, you know? When you have the right chalk.
You like chalkboards or marker boards better?
Marker boards, exponentially better. But I hate markers because they die so stupid fast. And so, chalk, at least you know what you got. And you're guaranteed to get this much out of it.
True.
Marker, you can take that lid off and get halfway through writing one proof and want to throw it away and get another one. So, I hate chalkboards. I hate working with chalk, and if I had an infinite supply of markers, I'd just use whiteboard. But I don't. So we fight with chalk. Whisper. Did we already talk about? Yeah, we did. Okay. So let XD be a metric space, then U is open in the topology induced by D, if and only if, for every point in the set, there exists some delta such that, let me say this a different way and then we'll read that. If and only if for every point in the set, I can create an open ball around that point without going outside the set. So pick some U, maybe can't do that. Pick some U, something like that, there's our U. I want to know, is this thing open? We're going to say this thing is open if and only if for any point in there you pick Y, I can find a delta such that this ball, that was a terrible center, let's just draw the ball in the center. Okay, there's my Y. If and only if for any Y I pick in U, I can find a delta such that the open ball with that radius delta is a subset of U. Make sense?
Yeah.
And this, I don't even know that we need to write this proof, probably just saying it will be enough. I'll write it if you want. Going this way, let's pretend that we know that U is an open set in our induced topology. Then it's a union of open balls,
Yeah.
Yeah.
right?
Yeah.
And so every point in there was inside an open ball. Using this lemma, we can create an even smaller ball centered at that point.
Mm-hmm.
Did I lose you in that?
No.
That made perfect sense?
Mm-hmm.
Okay, going the other way. Let's pretend that U is a set, such that for every point Y inside of U, we can find a delta such we can find an open ball containing that point that's a subset of U. Well then by the union lemma, U is equal to a union of open balls, which makes an open set, because those open balls are basis elements.
Okay.
So it'll be like 2 lines each way. Think you got it? You want to see it?
No, I don't think we need to.
Okay. So, what are we doing now? Let dxy be the absolute value. Oh, the author just wanted to make sure you understood that our open balls still operate exactly how we've been talking about open balls before. So we're going to show that when we define an open ball to be the absolute value, x minus y, guess what? That's going to give us an open interval. Surprise. We've already talked about that, but let's make sure it makes perfect sense just in case. So let our distance function be the absolute value between x and y, be the absolute value of the distance between x and y on R. So we're talking about on the real number line, x is here, y is here, what's the distance between them? Take the absolute value and take the absolute value of the difference. Now if we think about an open ball,
The absolute value doesn't include actual points.
Oh, you're thinking wrong. Maybe I said it wrong, but we're talking about the open ball. So now let's think about what the open ball at x with epsilon is equal to. That is a set of all y's such that the distance from x to y is less than epsilon, right?
Yeah.
That's what it is by definition. So if we pick x right here and epsilon, why do I keep doing that? Epsilon is equal to this distance, whatever that distance is. What are all the points on the real number line within this distance of x?
One to the right, one to the left.
All the points from here to here, roughly, where this is x minus epsilon and this is x plus epsilon. Right?
Yeah.
Draw a line here, x minus epsilon. Draw a line here, this is x plus epsilon. All the points on the interval from here to here are the points in this open ball. So this open ball is the same thing as this interval. And that interval, if we let x be a plus b over 2, and we let epsilon be b minus a over 2, then we're just going to get it's ab. Notice that this is two equations with two variables. You don't know what a or b are, but you know x and epsilon, so you can solve it to find a and b. So we know that there are numbers that satisfy these two things called b and a. And whatever they are, when you plug this in for x minus epsilon, maybe it's worth doing one of them to make sure you see it. So if x is equal to a plus b over 2 and epsilon is equal to b minus a over 2, then x minus epsilon is equal to what? A plus b over 2 minus b minus a over 2, which is equal to, we have a minus negative a is going to be 2 a's. You see that with our a's? And then b minus b is no b's. So 2a's over 2 is equal to a. So x minus epsilon, same thing as a. Similarly, x plus epsilon, that just switches to a plus. So the a's cancel out, not the b's. It's just going to be b. So now this interval is the same thing as ab, which is exactly how we defined our open intervals with our standard topology on R. So what was he saying? He's saying, look, this metric still just gives you the standard topology on R.
Okay.
Pretty intuitive, right? Okay. In general, the standard metric on Rn is a Euclidean metric. So the same way we have standard topology, we also have a standard metric. What's a standard metric? Just a Euclidean metric. Euclidean metric, just flat out the way you already think about the distance between 2 points.
Okay.
Okay. So let's talk about one more interesting metric, just so you can see not a simple example. Jake's not here and Alice isn't here, so this isn't going to reach as much of the class as I hoped, because only Emma's seen an integral before. But we'll try to get to a filtering intuition. Before we do that, just for your guys' sake, give you a notion of what an integral gives you. So let's say that I've got some function f, and it's just some function like that. Here's f. This right here on the number line is a, this right here on the number line is b. With me so far?
Yeah.
Pretty straightforward.
Mm-hmm.
Then this symbol, the integral from a to b of f, and if we call this function f of x, then we can also call f of x here, doesn't matter. The integral of the function f of x dx, ignore the dx, but the integral of the function f from a to b just gives you the area under the curve. So that equals whatever this area right here is. You with me?
Yeah.
That's all it is. So this gives you the area under the curve. Okay. So now that we talked about that, let's talk about this. So let C with the closed interval AB be the set of all continuous functions of the form f from AB to R. So let's get a picture of some of these to help it make sense, because this is an infinite set. So here's A, here's B. What is a continuous function defined on this interval? Here's one. Is that function continuous?
Yeah.
Did I have to pick up my pencil anywhere when I was drawing it? No, there's no holes, there's no jump. There's one continuous function defined on that interval. Here's another one. 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 Okay, there's infinitely many of them. That's our set. The set of all these functions.
Okay.
With me so far? So this is a set of all the continuous functions you can create on this interval. Okay, now our metric. So given two functions, f and g, we're going to define our metric. We could have used a d here, but it's common to use rho. The distance from f to g, we're going to define as the area between the two curves. So here's one continuous function from a to b, f. When we take its integral, we would have gotten all the area underneath it.
Yep.
Here's another function, g. When we would have taken its integral, we would have gotten all the area under it. And now we're taking the absolute value of their differences, of the difference of the two. So that's going to make sure that something like this is positive. So our difference is always going to be positive. We don't want to just do f minus g, because we want it to still be positive if g's on top. So this just makes sure it's always positive. This is only 0 when there's 0. I'm talking about inside. So imagine that we plotted this function f of x, the absolute value of f of x minus g of x. What would that look like? That would look something like this. So this is just the two functions. Now I'm plotting the function f of x minus g of x. So don't be confused by what this is. So f of x minus g of x, absolute value. So what's the height of this minus this? That's about this high. What's the height here? That's when it's 0. The difference between the two functions here is 0. The distance between the two functions here gets pretty big. I mean, that's like all the way, shouldn't have put this point so high. This point's a little lower, this point's a little higher. We go back down to 0 here, and then we go up again like that. So if we plot their difference, it's going to look something like, it's going to be terrible, but we'll try it. Something like this, this, where's my 0? I missed my 0. This. There's our difference, right?
Okay.
And now, this is just saying the area of their difference function. That's the area of this thing, and this thing. That's the same thing as this area, and this area. So it just gives you the area between the two functions. So there we go. And that's going to be a metric, because the area is only going to be 0 if those functions are the exact same function, right?
Yeah.
So it's going to satisfy all those properties that we have over there. But there we go. So we have a way of talking about a distance between two continuous functions on some closed interval. There it is.
That's cool.
This cool. And now we can talk about a topology on these things. We can talk about a topology on the set of all continuous functions defined on this closed interval. Because we can talk about a metric space on it. Yeah. So this is, once again, we're getting into those places where it's really hard to try and get any sort of intuition for what these things look like, feel like. How do you visualize a set of all continuous functions on a closed interval? And then talk about topology on those things. But writing it out, it's really not that
Metrics are
complicated.
things that we just went and defined kind of outside topology, and then we're using it inside topologies.
So a metric is just a function that satisfies these three things. We use metrics all over the place. And we use metric spaces all over the place. So a natural question is, can we get a topological space from a metric space? And then, do we get all the stuff that we talk about in topologies for free if we have a metric space? The answer is yes. And then the topology induced by P is called a function space. So the topology that you get from this metric is called a function space.
Alright.
Special name for that kind of topological space. But yeah, that's it. Nice short class.